Hello guys, hope you're doing well, and as always, if you are new to my channel, I would humbly request you to subscribe to my channel and press the bell icon so that you shall be able to see all the latest videos that I will be uploading on my channel. Thank you. Okay, so the problem at our hand is that we have to study Mohr stress circle, and if you look at it, in the previous videos, we have already understood and studied the Mohr strain circle, and we have solved it on the MDS software to fully understand the Mohr strain circle. For the Mohr stress circle, we have two options. If you look at it, those two options over here on the extreme left side, if you look at uh, you can draw a Mohr circle by two techniques. In one technique is that you will take the rotation of your as anti-clockwise, and your shear stress value will be taken positive downwards. Okay, and the other way you will take the rotation of your theta clockwise as positive, and the shear stress value is taken positive on the top side of the vertical axis. Okay, we shall be considering this approach. We shall be considering this approach of the Mohr stress circle, as it is fundamental, because when we rotate our angle theta to theta in Mohr circle, it will be anti-clockwise, which will be matching our previous main assumption that anti-clockwise angles are positive. Okay, now to understand the Mohr stress circle, remember that we have this is not these two axes are not geometric axes. Remember that these are shear axes. On the horizontal axis, we have all the normal stress values, which will be sigma x1, sigma x2, sigma 1, sigma 2, and on the y-axis we will have the shear stress values and the maximum shear stress values on the y-axis. So remember, this is our assumption that we will choose. Then if you look at it over here, we will explain it in a very simple way. First of all, you have an element, okay? Before that, remember, Mohr stress circle is a very powerful analytical tool for engineers to use in order to calculate the normal stresses and shear stresses and their own orientation within the material. You can calculate them very easily. So it's a very powerful analytical tool. Apart from that, you could also calculate the maximum principal stresses on the Mohr stress circle, which will be helpful in designing of the materials, as they will respond to the yield of the material. So you should have to be below these values of sigma 1. Okay, and the other thing is that it can also be helpful to calculate the moment of inertias of the system. You can calculate the values of moment of inertia Ix and Iy lying on the x-axis, and the product moment of area lying on the y-axis for respective z sections and L sections. You can also use the Mohr's circle for calculating the moment of inertia. This is just from the knowledge point of view. Now, first of all, you will be giving this element, and this is going to tell you about the state of the stress. We will always start from this point A, okay, and we will say this normal stress value on it is given as sigma x. It can be any numerical value, just for explanation, and this is tau xy. Remember, this tau xy is very important. If this tau xy, this and this is showing you anti-clockwise direction, remember, take always the value of tau xy as positive. But if this phase A gives you a value of shear stress, and the orientation of the shear stress is taken as clockwise, if then you will take this tau xy as negative. But from our assumption point of view, on the phase A, we will always assume that tau xy is taken as anti-clockwise, and we will always assume that. Okay, but if in the problem they give you the other way around, then you have to take tau xy as negative. Okay, this is just from the explanation point of view. So phase A is basically telling you that there is normal stress on the horizontal axis sigma x, and the vertical is tau xy. These two actually are the two coordinates. Sigma x is the coordinate on the x-axis, and tau xy is the coordinate on the y-axis. Okay, remember this. In order to start, first of all, remember, you have to take the origin on the graph paper, and let's see, this is our origin on the graph paper. Now, once this is being done, then basically you have to calculate the center of this circle. Okay, in order to calculate the center of this circle, what you will be doing is that you will be calculating the average of this sigma x and sigma y and divide by 2. You will calculate the average of these two values. So this will be giving you the center of the circle. From here, you will first of all select origin properly. Then you will basically selecting a proper scale, and then from here you will move and calculate the numerical value of this over here and put a point over here. Okay, Remember, there is nothing over here. This is this one point and the other point. So from origin you go and you put a point over here, which is points at C, showing you the center of the circle. Okay. So once this is being done, now what you will be do, you will be plotting this two coordinates, sigma x and tau xy. When you move here, and if you look, you can move here till you go to this point, sigma x any value, you can say sigma x a value. For example, it is 8,000. For example, you can move here, here, here until you reach this point A. You see this point A. So this from here to here, it will be from this point. Starting from this point to this point is sigma x, and since tau xy is anti-clockwise, it is positive, and positive is downwards. So from here you will go down to this point. Okay. So here to this point, you can see they are saying you sigma x. Okay, here to here, this is sigma x, and this is tau xy, positive downwards. This is tau xy. So this first point is plotted. Now you will calculate the other point, which is the B point. Okay, this is sigma x, sigma y. So now when you go for the B point, again from the origin you move and you put, say sigma y has any numerical value which will be less than sigma x. If it is for so over here, as point B is there, for example, sigma x is, if you say is 8,000, then sigma y will be some 5,000, for example. So you move here and here until you calculate the value, and you put a point over here, and then you go above to calculate this tau xy, which is again clockwise, and clockwise is negative on the top from the assumption, from this assumption. So from here you go top and you put it up this, reach this point and put a point over here. Okay, so this is sigma x, sigma y, sorry, sigma y, and this is tau xy, but this since going up, this will be negative, and this point is sigma y. So from here to here, there was one point, you join this point to this point, and you join this point to this point. This is the diameter, diametrical line. Now you put the center of your compass over here, and basically once that is being done, you will basically draw a circle. Now this circle is being drawn. Okay, now once the circle is being drawn, you will have a lot of easier job from now onwards, because now this has been done. You have plotted this point A and you have plotted this point B also. You have joined them. Now the other target of you will be basically to calculate what will happen if this element is rotated by an angle theta. Okay, so if this angle, there are two choices. It can either be rotated anti-clockwise or it is rotated clockwise. If this element is rotated anti-clockwise, we will be moving from this origin of ours, from AC, we will be moving in the anti-clockwise direction. If they say in the question, they say for example, this element is rotated 20 degrees. So we will move from this point, from the origin, from this point. Okay, these values. The first origin is very important. Okay, we will be moving from this by an angle of 2 theta. If this rotation is anti-clockwise 20 degrees, this is 40 degrees. If this is 30 degrees for anti-clockwise, this is going to be 60 degrees. But if the rotation is clockwise, say we say it is minus 20 degrees. So from this point, we'll move in the clockwise direction, which is minus. So if this is minus 20, we'll move here from here to minus 40. Okay. And what we will do, we will put our protractor on this line and measure an angle 2 theta until on the circle you touch this point. For example, it is 20, so this will be 40. Okay. So you put your protractor here and put a point at 40 degrees and join this CD. Okay. Once this is being done, you can basically say this angle is 2 theta. Now you will be interested to calculate what is point D. Point D is basically, this is the point D after rotation. So for this point D, you have to plot these 2 points, sigma x1 and tau x1 y1. Okay. But if you want to plot these two values, you must know that this angle is 2 theta. Okay. And before that, you can also basically make an assumption that since this is 2 theta and you know this angle from here to here, this angle will be called as 2 theta p1. Okay. We are moving anti-clockwise, so we can measure from here. You can measure this angle, put your protractor here and also measure an angle, this angle. So this angle you already know by means of protractor is 2 theta p1, and this angle is 2 theta. If you subtract 2 theta p1 from 2 theta, you will get this beta. Okay. So in order to get the values of this D, which after rotation, you can basically know basically sigma x1 is, again, this angle is the radius of the circle, and this beta. Okay. If you know the radius and you know the beta, you can calculate the length from here to here, and you can calculate tau x1 y1 from here to here. As you already know, tau x1 from here to here will be tau x1 y1, and here to here it will be uh, from here to here the length will be sigma x1 y1. So this length will be radius cos of beta will give you sigma x1, and radius sine of beta will give you tau x1 y1. So simple calculations, simple trigonometric calculations. Okay, from here to here it will be r cos beta. This component will give you sigma x1, and r sine beta from this here, from there, this r sine beta will give you tau x1 y1. And you can see also from here, this point is tau x1 y1, and from here, if you look, this is sigma x1. Okay, once this is being done, you can, if you want, you can also calculate your d dash in the similar way, or you can just you have drawn this line from C to A. You can just extrapolate it by means of a scale to go back and project it. You will get d dash automatically. Okay, so this is being done. So our main job is done. Now we basically have to calculate. We already know this 2 theta p1 angle from here to here. This is the angle of the from the principal plane, 2 theta p1. If you want to calculate the other angle, this is the principal stress p1 at this point, and this is the angle of the principal plane from this AC is 2 theta p1. You want to calculate this angle 2 theta p1 plus 180. Okay, so this is, you calculate 2 theta p1, and then you add 180 from this point. It will be 2 theta p1 plus 180 will give you 2 theta p2. The other angle remaining is basically, if you look at it, is the shear, the maximum shear stress. Okay, so this is our main datum line. From here, if I move backward, I will touch these 2 points. Are basically these 2 lines, just to tell you, are the points of the shear plane. Okay, and this is the maximum shear stress value. And remember, this is going to be the radius of the circle. So in order to, this is point will be called as S1, plane of maximum shear stress S1, and this point is called as S2. So if we move backward, so this angle will be called 2 theta S1 from this datum AC. This is the datum AC. I move backward to here, it will be 2 theta S1. Okay, and but since we're moving it in a clockwise direction, it will be minus 2 theta S1. Okay, and if you want to calculate this S2, it will be again minus 2 theta S1 plus 180 will give you 2 theta S2. Okay, and just to tell you another thing, if you look this A, there's written theta equal to 0. Okay, and this here theta equal to 0, theta equals to 90. What is this actually? This A theta equal to 0 is telling you the condition of the angle of the element. This angle is basically at theta equal to 0. There is no rotation in this element. And if I move this element by an angle theta, say 20 or 30 degrees, this is tell you this is going to be that point D, theta is equals to some angle of theta. Okay, so your 30, this theta can be 20, 30, 40, and depending upon this, if this theta is 20, this theta will be 40. Okay, but this theta is twice showing to you, but this D is showing you the orientation of this theta. Okay, so remember, this is the orientation of, if this is 20, it will be showing you 20. If this is 30, it will be showing you theta as 30. But on the element, remember, it will be twice of this theta. It will be twice of this theta. Okay, so this is a very important assumption that you must know to correct your problem. Okay, and once this is being done, I think you can also calculate your principal stresses over here also. From here, you know, this is the average stress, and you add the radius, you will get sigma 1. And from here, if this is the average and you minus the radius, you will be getting your sigma 2. These are 2 very critical points. These are points of principal stresses, sigma 1 and sigma 2. Okay, this is the point of the maximum tau xy max, maximum shear stress. Okay, so once this is being done, now we can proceed to a numerical to understand this theoretical concept in a more better way. Okay, so this is a numerical. An element in plane stress at the surface of a large machine is subjected to stresses sigma x 15,000 psi, sigma y 5,000 psi, tau xy 4,000 psi. So this is what it is: sigma x 15,000 psi, sigma y 5,000 psi, tau xy is 4,000 psi. Now they have been telling you about this, but remember, this tau xy is very important. This is the point. Again, this is point A. and this is showing you tau xy 4000 as psi anti-clockwise. So our assumption is similar. We don't have to make any further changes. And if we plot it, first of all, we have to calculate the center of the circle. Say this is our origin, and the center of the circle formula, you know, it's sigma x plus sigma x plus sigma y divided by 2. From here I move and I put this point C over here. So 15,000 plus 5,000 divided by 2 is 10,000. 20,000 divided by 2 is 10,000. Then you plot this point. You plot this point, which is 15,000 and 4,000 on the graph. From here, again you move 10,000 plus you move 5,000. So this is like 15,000, and tau xy is anti-clockwise. So this is 15,000 and you move 4,000 downwards. So 15,000 and 4,000 downwards, this is your datum. Your datum is reached. CA is your datum. All calculations will be done from this datum, CA. Okay. Now what you can do is basically, you know, your element is rotated by an angle of 40 degrees. Okay. So what you can do, you put your protector over here, and since he says 40, so on the Mohr stress circle, you'll rotate it by, the angle you'll put is 80 degrees, double the angle. Okay. So remember, it will be double the angle. So at this point A, it was theta equals to 0. At this point, actual angle is 80, but this is showing the condition of the element, which is this. So this is theta equals to 40 for the element, and this is for the Mohr stress circle. Now you know this angle is 80 degrees. Okay. Now if you want it, basically if you know, you can also calculate this angle and this angle. Okay. How to calculate? This angle will give you the value of tau xy, and this value basically, and this is basically you have already calculated it. Now you'll be interested in calculating this point D. Okay. So you know this angle is 80 degrees, and if you want to calculate this angle, basically you know this angle is at 38.6. very easily you can calculate. If you know this is like 5,000 and this is 4,000, so you can take the tan of this and you can calculate 38.66. So 80 minus 38.66 will give you 41.34. Now if you want to calculate this value, the vertical, which is tau x1 y1, okay, what you will be doing is basically, you know, this is the radius, and you know this angle is 41.34 degrees. So it will be 6,403 sine of 41.34 will give you the value of which is called as the tau x1 y1. It will be, okay, it will be the value which is tau x1 y1. And if you want to calculate this value, which is going to be your sigma x1, so it will be again this radius cos of 41.3. So radius, you want to calculate this value from here to here. It will be radius cos of 41.34. So here you calculate your values of the normal stress and the shear stress. Okay, we have calculated the normal stress, which is sigma x1, and the shear stress is tau x1 y1. Now once this is being calculated, you know all these values, and you can just extrapolate it backwards to calculate d dash. The radius is very simple as you drawn it basically, and you can also calculate the radius analytically also if you want. You can, with this formula, it can be calculated analytically also to check whether you're doing it right or wrong. Okay, so now the other task for you at hand is basically to calculate the values of you know that the from this datum CA, the theta P1 is 38.66. Okay, and if you look from the other point of view, is that what is theta P2 will be, that is very important. Okay, so this is 38.6. remember, on the element it will be half of this, 19.33. remember, very important. Okay, and what will be theta P2? From here it will be just adding 180. If you add this 180, 38.66 plus 180 will give you theta P2. Okay, and if you know it will, you will get something like 38.66 plus 180 will give you something like 218.6. you on the element it will be 109.3. okay, so theta P1 plus 180 will give you this theta P2. Okay, now still, how to calculate the theta S1? The angle of the maximum shear stress plane will move in the backward direction. We will be moving from here in the backward direction. If you move in this backward direction, we'll be moving in this direction. We'll be moving in this direction. Okay, we're moving in this direction, and it will be since moving in the clockwise direction, so the angle will be 2 theta s1, this angle, but it will be minus. It will be minus. Why? Because this is 90 degrees. You minus 38.66 from it. It will be 90 minus 38.66 will be your required angle. Okay. So if you want, you can basically 90 minus 38.66 will give you an angle of 51.34. Okay. So on here it will be 51.34 minus 51.34. On the element it will be 2 theta s1 as minus 25.7. What about the other angle 2 theta s2? You will write minus 2 theta s1 plus 180. Minus 2 theta s1 plus 180. So you will be getting, if you basically minus 25.7 plus 180 will give you an angle of 154.3. Okay. If you look at it, minus 25.7 plus 180 will give you 154.3, and you divide by 2, you will be getting. So if you look at it from here to here, it is minus theta s1 is equals to giving you twice of 25.7. 25.7 into 2 is 51.4. Okay, so again you can see this angle will be 20. If you look at 25.7 into 2 is minus 51.4. From here to here it is minus 51.4, and you plus 180, you will get basically something like 128, and the total angle from minus here to here, and on the element it will be half of that. So 128.6, something like that, half of the element will be 64.3 degrees. Okay, so you get 2 theta s1, and then you add 180, you will get 2 theta s2. So this is how basically you calculate the angles of the principal planes and the principal maximum shear stress angles. Okay. So these are the analytical checks. If you want, you can do it. The other thing is that you can also basically, I have told you how to calculate sigma 1 and sigma 2. Is very easy. Okay. So this is done analytically. And the other thing that is very important here is that just to tell you, this has already been shown you in the calculations. This picture is already shown. If you look at it, it's B. This is just what we have calculated here. For this is the angle of the principal plane theta p1, and this 16,400 is the sigma 1 stress, and this is 3,600 is the sigma 2 stress. If you go back, okay, from here to here, if you add it, 10,000 plus 6,403, this is your sigma 1. And if you take 10,000 and minus the radius, which is 6,403, will give you sigma 2. So again, this is 16,400, and if you minus 10,000 from 6,400, you will get 3,600, and this is the angle theta p1 shown to you. Okay. So, and this is again the same thing what you have plotted here. They have shown you on the stress elements. This is very important to draw. And when you draw, this is the maximum shear stress. If you know that you have calculated it, the maximum shear stress is showing as 6,400 psi. And basically remember, this is your 10,000 psi. Why? Just to let you know, this point from here to here is the point of maximum shear stress, and its value is 6,403. But on the plane of maximum shear stress, there will be zero normal stress, but there will be one at this point. If you can, there will be always one kind of stress on the plane of maximum shear stress, and that is the average stress. From here to here, to calculate the average stress will be sigma x plus sigma y divided by 2, which is this. So whenever you're plotting the principal stresses, remember this is the angle of the principal plane 19.3. So when you are plotting them, you will always say this is 19.3, and this is the sorry, you're plotting this is your average stress, average shear stress. Sorry, this is your maximum shear stress tau xy, And these two, if you look at it, this is the angle of the average shear stress, which is 10,000 psi, and this angle, if you remember, it is theta s1 equals to 25 minus 25.7 for the element, because it is negative, you're going backwards. Okay, so if you remember that 25, when you were doing on the Mohr stress circle, the angle which was 51.4, this angle from here was 51.4, but on the element it is minus 25.7. Okay, so this is showing you the negative angle because it is clockwise. This is the average shear stress 10,000 psi. This is the maximum shear stress 6,400 psi. And if you look at it, this is anti-clockwise and this is clockwise. Okay, so this is how you basically calculate your angles. Just to let you know further, we can also solve this problem. I have done it before, but just for your information, we can double check it that whether we have done it right or not. We have like, all right. So just to let you know, after calculating all this, we already know this condition. I've told you once it's rotated, these are the values that have been calculated by us on the actual Mohr stress circle. Like this was the angle which has been rotated, and after this rotation, you look. This is normal stress 14,810 from here to somewhere. If you look at it, this point is 14,810. From here to this point is 14,810, and tau x1 y1 that was calculated from here, this basically 4,230 psi. Okay, so this is, remember, this is very important. This is just showing you how the principal stresses are being placed on the element. So remember, the value of the principal stress sigma 1 was 16,400 and sigma 2 was 3,600, and its effective angle is 19.3. Okay, so if you go back, this is from here to here, this is sigma 1, which is 10,000 plus 6,403, this radius, and this is sigma 2, which is 10,000 minus the radius is sigma 2. And remember, the angle of the principal plane in the Mohr stress circle is 38.66, but on the element it will be half, 19.3 is the angle. And what about this maximum shear stresses angles? So if you go again, this is the for the angle for the maximum shear stress. Just to let you know, is that this is the maximum shear stress, which is the radius, is basically coming as a positive anti-clockwise. And again, you see that on the maximum plane of shear stress, there is another stress which is 10,000 psi. Okay, what is this stress corresponding to? If you look at it, if you look at on the plane of maximum shear stress at this point, uh, there will be one stress which will always be there, and it will be the average stress at this point. So this is the value of the average stress on the plane of maximum shear stress, which is this. So this value is 10,000. So and the angle which is going to be given from here to here is minus 25.7 of the angle of the principal shear stress theta s1. 2 theta s1 will be 51 point something 4, and on the element it will be minus 25.7. So this is telling you minus 25.7, and this is what it is. You can also double check these values if you want to. If we go to, if you see, we can basically reset this, and you can double check these values, which is the values given to us as 15,000. Just remember, if just give me a break, I will. Okay, so we entered these values. Normal stress 15,000, sigma x, sigma y is 5,000, and tau xy 4,000, but anti-clockwise, so it's counterclockwise. We will compute it here. We will get the angle of principal plane. Now the rotation is on the graph is showing 80, but here we have to place it as 40. We place it as 40 and we compute it. So we get this rotation as 80, as we have told you in the analytical. The center of circle is 10,000. This is the radius. The principal stresses values are 16,403 and 3,596. Maximum shear stress is 6,403.1, and we can basically compute the angles of the principal plane at the maximum theta s1, the maximum shear stress angle theta s1. This is the angle of the principal plane, 19.33. It was 38.6, and this was the angle for the maximum shear stress, which is telling you as theta s2. And remember, we from here we went backwards, which was 51.4, and we add 180 to it. So we get something like 128, and on the element it will be half of that. And again, this is the values of the sigma sigma x1, and this is the value of tau x1 y1. Okay, sigma x1 was 14,807, and this is sorry, sigma x1. This is sigma y1, and this is tau x1 y1. So sigma x1, if you go back and see, sigma x1 is 14,807. If you look at it, 14,807, and sigma y1 is 5,190. It is 5,190, and tau x1 y1 was how much? 4,230. So it is 4,230. So this is how we have today in this lecture of ours. We have studied what is a Mohr circle, how it is being plotted, what are its assumptions, and then we have taken an analytical problem, we have solved it, and then we have also simulated that same problem on MDS to understand the concept better. I hope this video will be beneficial for you, and in the end, I thank you all guys, and I hope you have a wonderful day. Bye.